Good morning, everyone. Hello and welcome to today's webinar on Hyperspectral Imaging Introduction and Challenges in Field Airborne Applications. Thank you for taking time out and being here today. Hope everyone is safe and doing well in this difficult COVID-19 situation. We are trying our best to contribute in every way possible in such situations. I am Shilpa Ramesh from Sincel International. I am working as a sales and service engineer since 3 years in this company and I will be hosting today's session. So, a little about Sincel International. Sincel International is a pioneering company in marketing and servicing of highly sophisticated overseas products for India. The company is promoted by scientists and technocrats who are having more than 25 years of experience in instrumentation sales and support. Sincel International was started in the year 1995 to serve the scientific community. The operation started at Baroda and within a short span of time, it started its branches all over India. We have 7 branches across India with 35 employees. We deal with a variety of products ranging from hyperspectral imaging cameras to spectroradiometers to spectrometers. So, in today's session, our first speaker, Dr. Casey Smith, will be talking about hyperspectral remote sensing and resonance imaging hyperspectral airborne system, followed by hyperspectral machine vision and OEM solutions. Then the webinar will be taken over by Dr. Adam Stern, who will talk about Pushbroom hyperspectral imaging and snapshot technology and how to choose the right hyperspectral instrument, which will be followed by a question and answer session. So this was about the webinar. At the end of the webinar, we will be sharing a feedback form. Registered members who want the certificate will notify it in the same form. If you have any questions, kindly type in the comment section below. We'll take up all the questions in the question and answer session at the end. Now Dr. Adam would like to just introduce about Resinon and a bit about Resinon. Then we'll start with Dr. Casey. So I'm adding him. Good morning, Dr. Adam.
Great. Thank you, Shilpa. Thanks for hosting Casey and I, and thank you, everyone else. I just want to introduce Resinon. We design and manufacture hyperspectral imaging cameras, and we have been with Sincel International for almost 10 years now. They're great partners for us in India. Casey and I both work at Resinon. We've been here. Casey's one of the founding members of Resinon and chief scientist and principal engineer for remote sensing products. And I've been with Resinon for 10 years. And so we design and manufacture hyperspectral cameras. And they cover the visible and the infrared spectral ranges. And we've got some that go off into the ultraviolet. These are Pushbroom line scan imagers. And we integrate these cameras into complete systems, complete hyperspectral imaging systems for the laboratory and for outdoors. In the laboratory, we have a system that can measure reflectance or in transmission. The outdoor field system sits on a tripod. And then today, Casey is going to talk to you about our airborne remote sensing system, which provides geo-registered hyperspectral data. A quick little bit, just very briefly about Resinon. Most of our sales are outside the U.S. About 1/4 to 1/3 of our sales are inside the U.S. Our largest markets are in Asia, China and Japan, Australia. India is up there as well. And then this graph right here just shows that we sell to customers all over the world. And we sell to research customers, research professors in academic universities and in government labs. Research systems to research professors and researchers are the majority of our sales. So Resinon is a small optics company. We have 16 employees. We've been around since 2002. We're located in Montana in the USA, which is close to the Canadian border. And it's up in the mountains. Here's a picture of our town, and here's the university. And Resinon is a vertically integrated company. We do everything ourselves. We do our own optical design and our software development. We have our own machine shop. We do our own integration. We do it all. And that allows us to really be able to support our customers and keep our prices low. And then It's worth noting that our instruments are high precision, they provide high resolutions, quality scientific grade data, and we provide complete systems that have all the hardware and software you need to acquire hyperspectral data. And I think, one or two more slides. At the end of these talks, if you're interested in learning more, you can go to our website and you can download sample data for free along with our data analysis software. And so if you go to our website and go to the downloads page, you can get the software and the sample data. And the data is in standard binary formats, so you can access it with our software or any other software tool, such as MATLAB or NV or Python or whatever you of course, if you have questions during this webinar, please stop and let us know, and we'll spend as much time as you want afterwards to answer questions. And then after the webinar is over, feel free to contact us at Resinon or our friends at Sensil, and we're here to answer any questions that you might have. And we can talk about more details later on, but I think now is a good time to go to Casey and have him tell us some details of our airborne remote sensing systems.
Thank you for the brief introduction about Resinon, Dr. Adam. Without further ado, I would like to introduce Dr. Casey Smith. Dr. Casey Smith is our first speaker, and then he is also one of the founders of Resinon. He helped to find Resinon in 2002, and is Resonon's chief engineer. He is the lead engineer on airborne system and machine vision systems. He earned a BS in physics from Montana State University and a MS in electrical energy engineering from Massachusetts Institute of Technology, MIT Boston. So I would just add in Dr. Casey Smith for the webinar. Good morning, Dr. Casey. You're live.
Good morning, everybody. Thank you for the introduction. I'm going to run through some brief slides about our airborne hyperspectral systems that we offer for both UAVs and manned aircraft. And then I'll run you through a short live demo of the software and the data that our systems produce. First, let's take a quick look at this video that shows one of our systems in operation on a UAV. And there's no sound to this video, so I'll narrate as we go. Here's a look at our system on a gimbal on a UAV. We provide the entire system, the hyperspectral imager, the data acquisition computer, the GPS IMU, as well as all the software you need to get it started and to do the processing of the data once it's collected. This video is taken at a farm outside of our offices here in Bozeman. Most of our sales are for agriculture and ecology applications. And if you notice, the data that I'll be presenting is from the same flight. So notice some of the agricultural products that you see there, some pumpkins, some kale, some cabbage. Like I said, the system is complete. It contains everything you need outside of the UAV to get started. And a lot of words on this slide, I apologize, but a few concepts that you need to understand. One is the concept of downwelling irradiance. That's simply the light that's coming from the sun, as all of our work from the air is illuminated by the sun. We have the at-sensor radiance, is the light that our sensor collects. And then at the bottom there, you can see a little cartoon of a tarp, which is our reference tarp. But the concept of reflectivity is what most people are trying to achieve when they're taking data from the air. They want to know the physical property of the object on the ground. And there's lots of ways to get to reflectivity. Some people even work in radiance without going to reflectivity, but our software and our system is capable of going to either radiance or reflectivity as desired. Most of our applications, as I said, are in agriculture, plant health, ecology, weed identification. There is some work in the NIR and the SWIR for mineral identification and anomaly detection as well. The Spectron software is the post-processing software that we use not only for our benchtop and outdoor systems, but also for post-processing our airborne data. It's very capable of converting all the data to the products you need, whether it's radiance or reflectance. It georectifies the airborne data so that you have latitude and longitude coordinates for every pixel in your data cube. And we try to make it as easy and as simple to use. So now I'll switch to the software demo, and we'll run through some of that data. I already have a data cube open, and this is the same field that you saw in the video. And as you can tell, it has some squiggles from the motion of the aircraft, and we'll georectify that in a minute. But first, let me grab, you can see under my cursor, you can see the spectra of every pixel in that image. So that's the power of spectral imaging, is that we have a full reflectance spectra for every pixel. The first step normally is to convert to radiance, which we do with calibration that we provide here at the calibration lab. This will just take a second to convert to radiance. Now we have units of radiance, which is both a function of the solar illumination and the reflectance of the object underneath us. The second step, we could convert to reflectivity or reflectance, but for brevity here, I'm going to georectify this data cube so it looks a little bit more normal to our eyes. And it also assigns a latitude and longitude to every pixel in that image. So we have to enter a few parameters here. One is the altitude of the ground, since I don't have a digital elevation map for this data cube, but you can use a DEM if you have one available. And then we just enter a few more parameters. This process also takes a little bit of time, but at the end we'll have a georectified data cube that contains the latitude and longitude of all the pixels. There we go. Now it looks a little bit normal. You see these sort of jags in the image. That's where the aircraft was disturbed by a little bit of turbulence or some wind. Fairly normal, but luckily our GPS IMU can take care of that. Let's zoom in here. We can see some pumpkins, I believe, that were growing in this field, and a lot of other agricultural products that were growing in this farm. So now, just to demonstrate, we're going to try to find all the kale in this image. And I have a spectrum that I created that's the reflectance spectrum of kale. And you can see that that's not quite right. So we can tune that down rather. Maybe a little bit more. And now you can see we have an algorithm. This is the spectral angle mapper that's found all the kale that it thinks it's growing in that field. And let's jump back up to this again. Another thing that we might want to do is look at a variety of different agricultural algorithms. we try to maintain a fairly exhaustive list, but we'll just do NDVI, which some of you may know is fairly standard output product that shows the relative health of all the plants in this image. Or we could simply put a threshold on this data cube and have it show only the healthiest plants. And so something like this might be useful if you were trying to determine where you needed water or fertilizer. The white pixels in this image would be the healthiest plants, and the black regions would be areas that needed some attention, or rows or roads in between. So that's just a brief demo of how you might process some of this data. But as you can see, it's quite simple and easy to process this data, producing a variety of output products, all georectified. We try to make this system as simple and easy to use as possible for anyone from farmers to PhD scientists at the university to use. So that's what I have for my presentation right now. We can certainly talk about anything that you've seen, and we can also talk about machine vision and OEM products as well.
Yes, you could talk about machine vision.
Okay. So the machine vision and OEM markets for us are very interesting, is that in that we can sell a lot of different or sell the same instrument to the same application over and over. But one thing that is a little bit difficult about the machine vision OEM markets is that we need a strong partner that can write either some integration software or can do the support that's necessary for these industrial applications in India. So we have lots of different ways that we can enter that. One is that Resinon, we obviously write a lot of software ourselves. That's one pathway forward, but probably more applicable to India is we have SDKs available to help people write machine vision or OEM applications based on our systems. And we also offer very good support on that SDK to help people enter those markets. Because normally you can take the data from our system and process it. We can help you there, but the end, the last mile there is to connect to either some other industrial application, some industrial robot, or sorting equipment, and that's where we need all that software is very application dependent, and that's where we need somebody, OEM or a machine vision integrator to take that last step. But in terms of the hardware we can provide all the spectral imagers, obviously, the lighting that we need, and then, like I said, support on the SDK to help that process move along. Adam, do you want to say anything more about OEM and machine vision?
Sure, I'll just add him in the seat. I would just like to thank you for the insightful presentation. I'm very sure each one of us was very benefited by the detailed presentation, and we could see how how the software is, how we can do the georectification, and how easy it is. So I'll just add Dr. Adam in the field. So before that, I would just like to introduce Dr. Adam Stern. So he is the second speaker for the day. Dr. Adam Stern did his BS in Physics and Mathematics from University of California at Santa Barbara and a PhD in Physics from Montana State University. Dr. Adam joined Resinon in 2009 as a senior scientist working on research projects. He is now the senior scientist and vice president of sales and marketing. So I'd like him to take over the session now.
Great, thank you.
Good morning, Dr. Adam.
To continue on with what Casey was saying, certainly hyperspectral imaging can be used to differentiate different materials and different commodities of different grades. So for example, in this slide here, you can see that different pharmaceuticals have clearly different spectra and are therefore easy to classify. This is an infrared spectral range. So even though the pills are white to human eyes, the different pills are easy to detect using spectroscopy, and imaging spectroscopy. So we can certainly provide the cameras, and we can provide the illumination, and we can provide, like Casey said, the SDK for the cameras, which is the software driver for the cameras. The trick with machine vision is converting the hyperspectral data to useful information. And that step needs to be taken by either the customer or an integrator company, learning how to convert the hyperspectral data to useful commercial information. And once you have that step, then you have to develop the software to take that information and then move robots or actuators or record data. So Resinon can help with the hardware and the SDK, and we're happy to support all of that. And especially in India, an integrator company or the customer needs to finish off that step of converting the hyperspectral data to useful information. Let me jump back a little bit and talk about a few different kinds of hyperspectral imaging. And then, yeah, here we are. And then I'm not certain all who is in the audience, but if there are some people that are interested in remote sensing, our system is very good at correcting for illumination effects, the Airborne system, correcting for illumination effects, both with a calibration tarp and a downwelling sensor. And Casey has some very impressive, a very impressive presentation about correlating those two sources to obtain reflectance accurately. And so I don't know if the audience is interested in some of those technical details, but if they are, and now's a great chance to learn about that. But let's go back. So Resinon makes Pushbroom imagers. These are line scan imagers, where each camera frame is a single line of data. And then the way you build a full two-dimensional image is you stack those lines next to each other. You translate the camera relative to the subject, for example, by flying over a field, the subject, with a drone or an aircraft. And you stack those lines next to each other. There's a lot of hyperspectral cameras on the market that use this Pushbroom approach to imaging. And then there's an alternative approach to imaging called Snapshot Imaging, where each frame is a complete two-dimensional image. And this is achieved by putting micro filters, optical filters, on top of each camera pixel. And so each pixel just measures one spectral channel, and they take many of these pixels and put them together to form one spatial pixel. This snapshot imaging is more convenient than pushbroom imaging, but it has lower resolutions and precisions. Let's discuss each one in turn. So pushbroom imaging, which is this line scan imaging, it's generated by placing a lithographed optical slit at the front of the camera and just letting a single line of information through to the sensor. And at the sensor, one dimension is spatial information and the other dimension is spectral information. The advantages of this pushbroom imaging is that it has higher spectral ranges, higher spectral resolutions, and higher spatial resolutions. And the disadvantage, of course, is that requires extra hardware. You have to translate the camera relative to the scene. You need a GPS IMU and some georectification software if you want to make a good picture. So you need extra hardware. The camera, a snapshot camera can just hover in place and take a picture, but a pushbroom camera has to sweep over the subject, and it can take a while to make a full scan. Snapshot imaging is easy to use. It has potentially shorter scan times, and you do not need extra equipment. But like we mentioned, they have lower spectral ranges and lower resolutions. And correcting for solar illumination can be difficult because each image, in one image, you'll have different angles in your field of view. And the viewing angle, let's see, the spectral results is heavily dependent on your viewing angle. So correcting for these viewing angle issues can be difficult with snapshot imaging. And then also, here are some, and also there's significant overlap between these filters on the pixels. Here are some graphs of some snapshot sensors. These are a little bit dated now, but they serve to illustrate the concept. And you can see between these various filters, there's a significant amount of crosstalk. So that really reduces the overall dynamic range and the SNR that you can achieve with these instruments. So that's pushbroom versus snapshot imaging. I will go through very briefly what some of the important parameters are when looking at hyperspectral cameras, when comparing hyperspectral cameras, and then we'll hand it off to Shilpa and any questions you all might have. So when you're shopping for a hyperspectral camera, obviously the most important specification is the spectral range. And these come in a few standard ranges, although of course there's debate on the exact numbers of these spectral ranges. But there's the visible, which is 400 to 700 nanometers. There's what we call the VNIR, the VNIR, visible plus near infrared, and that is the visible plus a little bit of infrared, up to 1,000 nanometers. There's the near infrared, which goes 900 to 1,700 nanometers, and then there's what we call the SWIR, short wave infrared, and that gets up to 2,500 nanometers. And then using a totally different technologies, you can get into this mid-wave and long-wave infrareds, and these are your thermal bands, or where you can detect gases. If you're only interested in the visible or in the near infrared, up to 1,000 nanometers, your sensors are all based on silicon, and so they are inexpensive, and the cameras are the hyperspectral cameras are relatively inexpensive. And then the near infrared cameras, they use indium gallium arsenide, and the cameras can get pretty expensive, and so the hyperspectral camera prices increase. And then if you move off into the SWIR, then these cameras become exorbitantly expensive. But there's a lot of interesting spectral ranges up, a lot of interesting spectral features up in this range, and so some customers may be able to absorb the prices here. So a secondary level of specifications are the basic resolutions, the number of spectral channels, and the number of spatial pixels. This tells you the quality of your imaging. Obviously, the more channels and pixels, the better the image. Make sure you look at the F number, which is the optical aperture of your hyperspectral camera. Very similar to a normal camera, that the lower the number, the more light that gets into the system. And the more light that gets into the system means a better signal, higher signal to noise ratio. Some of the hyperspectral cameras on the market are very slow. Our airborne hyperspectral system under sunlight conditions will operate at about 100 to 120 frames per second. And Resonon's spectral cameras can go much faster than that, between 200 and 500 frames per second, depending on the application. Some of the cameras out there, though, their maximum frame rates are well under 100 frames per second. So if that's the frame rates you're using, it's going to take a long time to do the scans, and there's a chance that they might not be appropriate for airborne remote sensing. And then, of course, for airborne and remote sensing, weight and size are important, especially if you're on a drone. And then price is always important, especially for research customers. One of the things that we found most important amongst for our customers is the support for our customers and our distributors. And so Resinon is dedicated to providing as good a support as possible. We're always here for the distributors and always here for the customers before and after the sales. And we're here for any help you might need. So that's pretty important. And so that's all I've got on this, Shilpa. Any questions or comments?
Sure, Dr. Adam, that was a very nice presentation by you. So there was one question, which was, can you elaborate on hyperspectral applications on mapping of soil types, weathering products, clay types, and how the soil moisture affects correction interpretations?
I do not know the answer to that question. Casey might have some information, but we at Resinon do not do research on these topics. We used to. Resinon used to be a research company, but now we just make the equipment that provides the hyperspectral data, and it's up to our research customers to use the data to look for the results and their hypotheses. I do know that soil science is a very hot topic for hyperspectral imaging, and there's a lot of research going on using that. In fact, I know of some over in Karagpur. Casey, do you have more information on soil science and hyperspectral imaging?
Well, we can definitely detect moisture in the soil with the near-infrared system. We can detect the effects of moisture in the health of the plant in the visible and near-infrared as well. I would guess that in terms of soil types, that the near-infrared would be the most valuable spectral range to do much science on the soil type. But moisture, as I said, can be detected directly in the near-infrared and indirectly via the health of the plant in the Wiener.
Yeah. So the next question is, What is the data difference between hyperspectral versus multispectral camera?
I've got a good slide on that, Casey.
Great.
Here. Shilpa, can we show this slide right here? Very good. Okay, so in hyperspectral imaging, well, let's go back. Let's start with multispectral imaging. Multispectral imaging has been around since the 1970s with Landsat. In fact, multispectral imaging is a few spectral bands. Typically, they are discrete and they're separated. So, for example, so this slide shows a hyperspectral image from the flight that Casey was showing the data from. It's the same farm. And here on the right are our hyperspectral spectra from these three regions. And these curves here each have 281 spectral channels. So there's 281 data points from 400 to 1,000 nanometers. And all of the data points are adjacent to each other. Basically, we have a continuous spectral curve. Hundreds of data points. That's what hyperspectral is. Hyperspectral imaging. It's hundreds of data points effectively making a continuous curve. Whereas multispectral is a few spectral data points, maybe up to 10 or 20 spectral bands. The bands are typically fairly wide, and then they're separated. Like you can see, oops, sorry. Like here, you can see the bands are separated on the left. The graph on the left is made from the same data that the graph on the right is made from. And then these are, the graph on the left uses what the bands are in the Landsat satellites. So you can see obviously that hyperspectral data gives a lot more information than multispectral data and allows you to make a much more precise and refined model of your subject. That being said, in some systems, you do not need hyperspectral data. You don't need all of this information. And maybe you can get away with just a few spectral bands. So it really depends on your requirements. If you want to make a detailed model that is sensitive to small changes, then hyperspectral information might be your best bet. But if you're just looking for the existence of a particular mineral or a single species of plants, you might be able to get away with a multispectral solution. Some of our customers use our hyperspectral cameras to determine what are the important spectral bands, and then we'll move to a multispectral solution. So that's the difference between hyperspectral and multispectral imaging.
Yeah, so the next question is, I'm just showing it on the screen. Does Spectron allow band averaging using user supplied RSR and SRF?
Casey could probably answer this better than I.
Sure.
Sure. Spectron allows band averaging in a boxcar manner. I'm not sure. Our spectral response function is fairly uniform across the spectral range, so I think boxcar averaging would be a good way to tackle that problem. I'd be curious to hear maybe offline if you could email us if you wanted band averaging as a function of the spectral response function. That's probably something that we could do, but like I said, our spectral response function is fairly uniform across the spectral range. So I think boxcar binning is probably going to work just fine for that. But feel free to email us, inquiry@resinon.com or support@resinon.com with any of those questions, and we can answer them in more detail.
So the next question is, I'll just show it on the screen. How to decide bandwidth and central band in any instrument?
Right, I'll take that one also. The data cube metadata contains the center band. We correct for the second order spectral response of our instruments, so that when our software reports the wavelength of a band, it is the center band, and also the bandwidth, like I said, is also fairly uniform across the instrument. So you can trust that bandwidth doesn't change that much across the spectral range of the instrument. Go ahead, Shilpa.
So the next question is, any urban applications possible which spectral range is good for urban materials?
Yeah, we've done a little bit of work. As Adam said previously, we don't do a lot of that research ourselves. We supply the hardware and the software for scientists to do that research on their own. We have had lots of interest in people identifying urban materials, such as shingle, the composition of shingles, asphalt versus concrete versus vegetation. All of that's possible with our system as well. And like I said, if you have more specific applications, feel free to email us with those, and we can see if maybe we have some data that you can look at, or if we've had any other customers that have done that work themselves. Go ahead, Shilpa.
One more question for you. Suppose I want to analysis of water condition, then which sensor is the best?
We've had a few customers, I guess, looking at water condition, and I'm not entirely sure what that means, water condition, but I'll take a few guesses. One customer that's looking at algal blooms in lakes in the US, and that spectral range would be the visible and near infrared, as algae on the water shows up very well in the visible and near infrared. If you're looking at water itself, the near infrared range is more useful to detect water itself. And then we've also had some applications where people are looking at underground water, tracking pollution plumes underground by looking at the health of the vegetation on the ground. And in that case, it's the visible and near infrared that would be most useful. Shilpa?
So the next question is, why Spectral Pro software can't work on Linux system? Is it possible to install on Linux OS?
Right. At the moment, it's just a Windows application. Sometime in the future, we might look into porting it to Linux. But our software team is very busy adding new features and trying to make the software as best it can be. And at the moment, it's limited to Windows.
Please elaborate how hyperspectral noise can be reduced at software level.
Sure. A couple of different tools that are useful. One is binning or averaging of adjacent bands. A lot of times your application doesn't need the full resolution of the instrument, and signal and noise is more important than the spectral resolution. So at that point, you can bin or average adjacent bands to reduce your noise. Another tool that we find really powerful is a Savitsky Golay filter on top of the data, which that tool preserves the first derivatives, preserves a lot of the information that you're interested in, but reduces sensor noise as well. And that can all be done inside of Spectron software.
Is it mandatory to use reference reflector for every image?
No, not at all. And actually, let me show a little demonstration of that. I think everyone can still see my screen. Is that right, Shilpa? So here we have a data cube that contains the TARP, that we know the reflectivity of this TARP. And in this flight, we also have a downwelling irradiance sensor on board the aircraft. And so what I'd like to demonstrate here is how to use both a downwelling irradiance sensor and this reflectance TARP to produce kind of the best of both worlds. The downwelling irradiance sensor, if you operate it on board the aircraft, it monitors the changes in the downwelling irradiance from the sun as you fly. But because it's an additional sensor, it adds its own uncertainty and its own noise. The TARP on the ground is very nice because now we have this standard that is the most accurate way to convert to reflectance. But as the question points out, you don't always have this TARP in your data. So in this case, what we're going to do is we're going to use both the downwelling irradiance and the TARP so that you correct for the sensor noise of the downwelling irradiance sensor, and then you can apply that to your entire data set. So the first step here would be to convert to reflectance via the downwelling data. And for that, we need both the calibration of the sensor, which we provide, and the calibration of the downwelling irradiance sensor that we provide. So this will get us to units of reflectance, which I said has the advantage of you're monitoring the downwelling irradiance from the sun in real time, but has the disadvantage of the additional noise and uncertainty of using a second sensor. So to correct for this, we'll take this TARP and we'll create what we call correlation coefficients. And this uses the factory measured reflectance of this TARP. And now over here, we've created these correlation coefficients. So now if I go back to the original data cube, I'll do this process again. And in this case, you wouldn't use it on the same data cube. You'd use it on all the other data cubes that you took during this flight that don't have the TARP in them. And this time we're going to check this box. And now it'll use that information to not only use the TARP information, but it'll also use the downwelling information. And so now if you have data that is outside of your TARP file, let me hide this. For all the other data sets in this flight, you can take advantage of both the downwelling irradiance and the TARP. So you don't have to always fly over a TARP to use that functionality. And now you can see we have this 24% TARP that falls off greatly over at 400. This is the reflectance of this TARP that was measured at the factory before it gets shipped. So it's a very powerful tool to be able to use both the downwelling irradiance sensor on board the aircraft and the reflectance TARP, so that you have both the accuracy of using the TARP, but the convenience of using the downwelling irradiance sensor. Thanks.
What is the height range of the drone? What is the spatial resolution at maximum height?
Great. The height range for the drone, there is no height range. We ship the system with the objective lens focused at infinity, which is good to from 10 meters up to infinity. So you can fly as high as you want. You can fly as low as about 10 meters. Everything will be in focus. In terms of the resolution at max height, like I said, there is no max height, so that's hard to answer. But we have a calculator that you can download to help you compute what your resolution is as a function of your height and the field of view of your lens, as well as a lot of the other parameters that are important when you're flying on a drone or an aircraft. So you can always feel free to email us those questions. If you have an application that requires a certain resolution, or if you have a ceiling on your UAV that you have to fly under, we can help you compute all those parameters. Let us know.
How to compare the data of imaging hyperspectral PKL and non-imaging hyperspectral, like a spectroradiometer and a hyperspectral data, how to compare?
Sure, that's a great question. The ASDs are obviously a very nice single point spectrometer, some of the best made. Our data allows you to have almost the accuracy of an ASD, but it allows you to have an image as well. So it's a huge advantage over taking tiny measurements on the ground with an ASD. Our system allows you to compute or to collect an entire scene of data at a time. The ASD, obviously there's lots of advantages to a single point system as well in terms of the fidelity of the data, but we do quite well in comparison, and we think that the advantages of imaging a scene versus collecting just single pixels or single points of a scene are well worth the trade-offs for that. Thanks, Shilpa.
Can you brief about using hyperspectral in field of applications in agriculture?
Sure. Of course, in ag and ecology, the red edge of chlorophyll is a very common feature that people use our system for. You can detect the health of plants or much earlier than you can by other means. NDVI, of course, is a very simple algorithm that doesn't take full advantage of our spectral resolution, but there's lots of other algorithms that take better advantage of our resolution. You can look at the slope of the red edge of chlorophyll, which is a very sensitive indicator of the health of that plant. Outside of plant health, of course, you can do species identification, whether you're looking for weeds in a crop field, or in ecology trying to differentiate what might be an invasive species versus a native species. There's lots of applications. Like I said, feel free to email us any specific question about your agricultural application. We can try to answer it for you.
What could be the calibration protocol?
Well, we ship our systems with two different calibrations. One is the spectral calibration, which provides you with the wavelength of each band, the center wavelength of each band. The other calibration that we ship is the radiometric calibration, which is how many photons per wavelength that system is sensing. And since we ship both of those with the instrument, both of them are applicable. If in the laboratory or the outdoor system, you can sort of calibrate to reflectance or reflectivity using some reflectance standard, whether it's a tarp or a piece of spectral on tile. That would be the third calibration method.
Is the signal to noise ratio of the imager is good enough for water quality parameters determination?
I am not familiar enough with water quality to be able to answer that question. Signal noise is something that we pay a lot of attention to, and I think our instruments are as good as any other instrument, any other hyperspectral imager for signal noise ratios. So it's hard to answer really application-specific questions like that, since we don't do a lot of the application research ourselves. But like I said, it's a parameter that we're very concerned with, and I think we compete very well.
What are the data acquisition parameters of hyperspectral PKL?
Those are all user defined. Our software allows you to define the parameters on your own, so you can control the binning of the spectral data on board. You can define your own regions of interest that you want the data to collect, or the system to collect data over. Those are all user-defined parameters. I'm not sure what other parameters you're concerned with, but you can set the frame rate of the system. Lots of parameters are defined by the user in our software. It's very fluid and flexible software.
In Airborne application, which is the resolution of hyperspectral imaging applicable, biomaterial normal imaging is high contrast. In imaging hyperspectral, how to analyze the chorus of disease. I think they want to talk about disease in plants and how to find by airborne system. I think that is what they mean.
Sure. Like I said, the red edge of chlorophyll is a very sensitive indicator of plant health. So any disease of said plant will show up very early, sometimes within hours, certainly within days, with our system. So it's really application dependent and what kind of disease you're looking for. But any infection or disease that can affect the health of the plant should show up in the red edge of chlorophyll.
The next question is how hyperspectral imaging is useful for detecting soil salinity.
Soil salinity?
Yes.
I don't think that I'm familiar with that application. I would guess that salinity would show up more in the near infrared than in the visible and near infrared, but that's an application that I'm not familiar with.
So, do you mean to say that for the salinity of difference in spectrum change, and that can be detected by the sensors?
Well, certainly if the salinity of the soil was affecting the health of the plant, we would detect that. In terms of detecting salinity directly, I would guess that you would see that in the near infrared, but it's not an application that I'm familiar with.
So the next question is if airborne imaging can be applicable for studying plant biochemical or physiological attributes.
Again, not an application I'm familiar with.
Sure. Then, is it possible to mosaic multiple hyperspectral scenes in this software as it is taking long or too long, sometimes 2 days to mosaic scenes in other softwares?
Sure, we have a mosaic tool built into Spectron that allows you to mosaic individual data cubes, georectified data cubes into a larger data cube. We recommend, I mean, it is a slow process and it takes lots of memory of your computer. So we do recommend that you convert to GeoTIFF first and then mosaic the GeoTIFFs. So normally the process is you convert your data cubes into radiance or reflectance. You process that data into the output product that you desire, some kind of results, and then you mosaic those results. It's a much faster, more streamlined process, and that is something that Spectron supports.
Can we reconstruct hyperspectral image dataset for regular machine learning algorithms?
I'm not totally sure I understand that question, but if you look at Spectron, we have lots of different machine learning algorithms already built into Spectron, so you're free to play with a whole variety of different machine learning algorithms on our data sets with Spectron software, if that answers the question.
Is it possible to display a single band image in Spectrum software?
Absolutely. It's as simple as using the single band image, and I can look at any wavelength I want just by sliding that slider around. Go ahead.
What kind of camera mounted on drones is optimal for recording differences in color like near yellow, near green in agricultural field for application of CV algorithms?
Well, I mean, I guess I would recommend the hyperspectral imager. If you're trying to differentiate between yellows and greens, I don't think an RGB camera would be sufficient. So I would recommend a hyperspectral system such as ours, I guess, for that.
Is it possible to study plant leaf crop disease using hyperspectral imaging?
Absolutely, I would say that that's the best application for our system in the airborne field is looking at plant leaf diseases, definitely.
What are the input details required for Resinon georectification?
Oh, you just need to know the field of view of the system, which is a parameter that depends on the specific lens that you've purchased from us. And then you need to know the altitude of the ground or have a digital elevation map created via LiDAR or some other means. And those are really the only parameters that you need to know for the georectification process. Everything else is automated using the GPS IMU that's on board our systems.
Vegetation health indices, what can you say about current accuracy from customers if it is claimed to work across species who got all the calibration data for that?
Again, I'm not a plant scientist, unfortunately, so I only know what our customers use the data for and what I've heard adjacently from them. I think that as far as I know, plant health is very species dependent, and so the indices that you would use, at least the standard indices, it returns a plant health, but only relative to that species itself. I'm not up to date to more modern techniques. I'm sure there are many ways to account for the plant health across species, but I'm not aware of them.
How the atmospheric contribution to the signal collected when using UAV-based system based data collection?
Right. So if you have, well, one advantage that UAVs have, I guess, is that they, at least here in the U.S., they can only fly at 120 meters is the maximum height that we can fly. So within that air column, the atmospheric effects are very small, just because there's not that much atmosphere between the sensor and the ground. So generally, our customers choose to ignore those effects, especially if you're using a tarp on the ground. Then you only have a single column. It's very small effects. Of course, that depends on the atmosphere, the conditions. If you have smog or lots of water, then you might need to look at those a little bit more carefully. But that's really outside of what we provide. If you need to do more than using a reference tarp or a downrolling sensor, then to correct those very small changes, we'd love to hear your ideas and feedback on doing that, but it's not something we currently do. Sorry, I didn't hear you on that. I might have lost audio. If you could repeat that, that'd be great. I still didn't hear that question. It looks on my screen like it's the atmospheric question as well that I just answered. Sure, I can answer that question. The question is, without onboard GGPS and using global DMs, which are typically 30 meter, how do you restore such a perfect picture? So the demo, the data that I demonstrated was not using a DEM at all. It was using the assumption that the ground is fairly flat, which most agricultural fields are fairly flat. So I typed in the elevation of the ground, assuming it was flat. If you have a DEM, you can use that as well. And as this question implies, most global DMs aren't very good. So if you want to use a DM, you have to have an accurate DM, which these days can be done fairly quickly using structure from motion or LiDAR. We will have, coming this fall, we will have a RTK GPS system, which will help our GPS accuracy quite a bit. So more information on that system to follow in the fall. But at the moment, like I said, most fields are fairly flat, so you don't necessarily need a DEM as long as you know the ground elevation. It sounds like my audio is not through, so let me restart.
Can you end the session? End.
All right, can you hear me again now? Looks like we have a question here. Hyperspectral image of vegetation stress versus ground truth. Can you please mention preciseness of your devices? We don't have the capabilities at Resinon to measure vegetation stress versus or via any other means. I know a lot of people use the outgassing of oxygen and intake of CO2, but we're not plant scientists, like I said, so I can't really speak to that. We provide the hardware and the software to do research and science, but we don't do a lot of that work ourselves. So I'm afraid I can't answer that question in much detail.
Dr. Casey and Dr. Adam, thanks a lot for your presentation. Sorry, Shilpa was having some issues, so I'm just plugging in myself. Thanks a lot for the questions. There are still many more questions we have. We will email you. And yes, thank you, everyone. You can visit our website for more details for the Resinon Hyperspectral cameras. And please fill in the feedback forms if you have anything else to say. Thank you, everyone.
Great. Thank you.
Yeah. Thank you, Casey. Thank you, Dr. Adamson.
Thank you, Ron. Nice to see you again.
Yeah.
I hope
Thank you, everyone.
Healthy and safe there in Delhi.
Yes. Thank you. I'm just ending the session.
Okay. Good night.
Bye, guys.
Bye.